Yeah, hi. My name is Paul Bowie. I'm from NASA Ames Research Center, and I have an instrument on the ER2. I also have the same instrument on the WB-57. In fact, I'm going straight from here to Houston on June 20th because there's another flight mission down there. Similar instrument on the DC-8, Global Hawk, Sierra UAV, a couple of payload. But the principle is the same. The measurement, the goal is to make in situ three-dimensional wind measurement and temperature and static pressure. Static meaning it's as if the airplane is not flying. It's like you're just stationary. Of course, the challenge is to remove the 300 miles per hour impact on the measurement, and that's what we're here to do. I've been here doing this going on 39 years, straight out of college. In fact, this is the airplane I started working on in 1984, and been on many deployments all over the world. So anyway, the principal measurement of wind is everybody knows it, sort of. You know, like when you rowing on a boat down the river, well, the river has its own direction, and you're trying to go another direction. So the wind is really just a difference between the airplane or your boat and the current that you're sensing. The problem here, of course, is you're flying at 300 miles an hour, so your air is also 300 miles an hour, and you're trying to derive of order 1 or 2 miles an hour. So you're subtracting two very big numbers. So the measurement of each one of those vectors has to be very precise. So our measurement, so let's see. This probe here is our temperature probe. It measures ramp temperature. This up there is measured the total pressure, and it's also serves as a backup temperature. These four holes here allow us to measure the different air angle. Because, for example, if the airplane is flying and there's no wind, the top and the bottom pressure are exactly the same. So it'll be zero differential pressure. But if, say, there's a little air down here, you would see the difference. And it's the same thing on the side. So top is up and down. This one is a side. And for static pressure, which is a measurement of like pressure that you're not flying, is along the side of the airplane. There's two ports on the side, which we measure the pressure. And in the Q bay is our INS. We have a ring laser INS and a tuning fork gyro system. And we also have backup GPS in the back. The data system is also in the back. The reason the airplane is, my instrument is, the airplane is really our sampling probe, as opposed to most of the other instruments where they have a self-contained payload. You can just take it out, bring it in a lab. Because our measurement is so dependent on the flow and the shape of the fuselage. So we're always part of the payload. The wind measurement obviously is the dynamical signatures. And we measure pressure and temperature in order to derive the wind measurement. But it turns out pressure and temperature is also very important for chemistry, because all the chemical reactions depend on the thermodynamic, and temperature play a critical role. Classic example is when we did the ozone experiment back in '87. The temperature change of order 0.5 degree Kelvin would trigger whether you get ozone destruction or not via the nitrification cycle. So the wind measurement do provide several things. One of the factors is to do model validation for a lot of the weather. I mean, over the years, the weather prediction model has been really improved, and our data actually contribute to a lot of that when they we fly, and at the end of flight, we give the data right away to the various organizations to put into their model. And then, of course, when you have turbulence, which is allow all this air mixing, and which a turbulence is really effective is wind, small wind scale.